So, assembly lecture number 3. In the previous assembly lectures, we looked at obviously assembling stuff, but we also looked at journal bearings or bushings or sliding bearings. So, a sliding bearing is basically where you have, if we look at it from the side, one component sliding on top of another component. Okay, so that's a normal journal bearing. But now what we can do is we can create a bit of a gap and add little rollers between these components. So the rollers would actually act to reduce the friction quite drastically between this component and that component. Because instead of one surface sliding over the other one, we have a rolling action. Okay. So that brings us to roller bearings. Just want to check the question quickly. I'm assuming this is for the CAD assignment. Sure, you can name it like it was named in the folder. Yes. 608 is a bearing size. I think 608 is a bearing with a 8mm shaft. Yes, 8mm inner diameter, 22mm outer diameter. The RS refers to the kind of seal that it has on. This is a rubber seal, not a fur seal. The 608 is just the part number. It doesn't really have anything to do with the fact that it's an 8mm bearing. Okay, so roller bearings. These have rolling elements to support the forces of the moving component. So instead of one having to lie on the other one and slide or drag over the surface, it simply rolls. Forces are transmitted from the moving surface through the rolling element to the stationary surface. These bearings are known for their very low effective friction due to the fact that the rollers only roll over each other, they don't slide over anything. Okay, so technically the friction coefficient between the little rolling element and the members is still the same as for sliding, but because we're not sliding, we're rolling, then we have effectively got a lot lower friction coefficient. Okay, just to quickly explain this forces thing. So, in the normal case, the force of the ruler, the transparent one, is just pressing against the green one. If we add rollers in between them, force goes from the transparent ruler through the one rand to the green ruler, unless it goes in underneath it. Okay, so force, I can apply a vertical force as seen from the side, and then it will still support the load. So the load goes from the transparent one through the roller into the green one. So the direction of the major load that the bearing is designed to carry can be determined by looking at the cross section of the bearing. Remember that the force is transferred from one surface, like the moving surface, to the rolling element, and then from the rolling element, the force is transferred to the stationary surface. There's no specific rule as to which side should be which, meaning the inside one can be rotating or stationary, or the outside one can be moving or stationary. There's no rule. So these bearings do come in various shapes to suit specific needs of the designer. The main thing to consider is the load direction, load severity, space restrictions, and so on. So to just quickly look at the standard ones that we're going to look at or use in MGC, the first one is just a deep groove ball bearing. So this is a deep groove radial ball bearing. I've got a ring on the inside that can rotate, and a ring on the outside that in this example's case is stationary. It could be the other way around, where the center one is stationary and the outside one rotates. So it depends on the application. So in this one, the force is transferred from the inside ring through the ball to the outside ring. So in this one's case, the force is mostly radial. Okay. It was a 1 rand. 2 1 rands. Okay, so radial ball bearing, because the force is mostly going radially outwards. The way this one is assembled is such that it cannot just fall apart by itself. So the inside and outside are always kind of assembled in a certain way that they can't split easily from each other. On the inside there is a little groove, which is hard to see, but on the inside there's a little groove. So the inside ring has a groove in it and the outside ring has a groove in it, and the little steel ball on the inside is then constrained between these two grooves. So that's why the grooves can't move too far apart and fall apart. Okay, so that was the first one. That is the radial or deep groove ball bearing. The second one is what is known as a taper roller bearing. So with this first one, let's quickly make a section view. So we turn it like that, and we cut it through the middle. So we look at it like that. So the outside ring is one ring, and the inside ring is a different component. Deep groove ball bearing. This next one is a taper roller bearing, and it can actually fall apart. Basically, this ring on the outside Looks like that. And then where this one had a ball, this one has a cylindrical rolling element. Like that, and then on the inside of that, okay, so on the inside it's got a cone as well. With this one, force is transferred from the inside ring to the ball, from the ball to the outside ring. With this one, the force is transferred from the one ring to the cylinder, from the cylinder to the outside ring. So this one is radial, this one is both radial and axial. Meaning you always have to have a compressive axial force to keep this bearing together. Otherwise, it will just fall apart. The third one is known as a thrust bearing. So this one has a flat disc with a circular groove in it. The other one has the same. And then these balls go and lie in the groove. So these are designed to carry mostly an axial force. Okay, meaning it has to be a compressive axial force. If it's a pulling force, it will just pull the bearing apart. So this is typically if you have a heavy machine that needs to be able to spin. Then you can use something like this. This is known as a thrust bearing. This one carries force from the one ring to the ball to the other ring. So this is for axial forces. I just want to check the questions. So the first ball bearing, this one on the left, the deep groove ball bearing is used in kind of wheel kind of applications. Yes, like a sliding door wheel can quite often use these kind of bearings. Skateboards use them. Many different things use them. So basically how they assemble this is, you'll notice there's a metal cage around the balls. So before the cage is inserted, all the balls can go to one side. And they are designed such that if you move all of them to one side, they occupy less than half of this total area, which means the center ring can move off center. So basically you start with the outside ring, throw in the balls, move them all to the side, put the inside ring in, move it to the middle, and space the balls around, and then you keep the balls in place with that metal ring. So that's how the bearing is assembled, that it cannot disassemble by itself. The tapered one can be used in something like a turntable, yes, definitely. the groove of the radial bearing is drawn on the inside. There the ball is, and it is lying in the groove. So just the inside ring on its own in an isometric section view would look something like that. Yes, center lines are needed. So remember, hatching is the same for each component. How many components do I have? These three things form an assembly, which is a thrust bearing. But there's one ring, there's another ring, and there we have 12 balls. So, or 13, 13 balls. So this is not one component, this is 15 or 16 with the cage, 16 different components. And we show components are different by means of showing different hatching on them. Okay, let me just quickly show you one other bearing type. This one looks very similar to the radial ball bearing, except that instead of having a groove for the balls to go in, this one is just flat on the inside, and it's got these cylindrical rollers. So a long cylinder can almost look like a needle, and that's why this kind of bearing is called a needle roller. And because there's no groove, it means the inside can pop out. So needle roller. So needle rollers do basically the same thing as the normal deep groove, except that thickness is more compact. So a needle roller can fit in a tighter space. If you look at these two, they have the same outside diameter, but the needle roller can support a much larger inside diameter shaft than what the normal deep groove ball bearing can do. But they do still carry a radial force. Interesting though with this one is radial only. Once you put an axial force, the bearing disassembles. So they can handle nice big forces, especially for the size or volume that they occupy. So yes, they are used in heavy loads, but not in axial loads at all, because then the bearing will disassemble heavy radial loads. Yes, a needle roller does give more stability, but the main advantage is more due to the compactness of the cross section. So for the same size outside, it can carry a much larger inside shaft. And just to put it in perspective, a bearing like this one can typically handle about 2.5 tons or so continuously on it. So you could literally support a whole vehicle on this bearing and push it around on that bearing. So for a thrust bearing, remember the force goes from the one ring to the ball to the other ring, from the bottom one through the balls to the top one. So this is a compressive axial force. Second bearing is a taper roller bearing. Definitely, these bearings will need either grease or oil to run correctly. Technically, for MGC, we're not going to specifically focus on the lubrication of these bearings. So we might have something like a grease nipple or something in application, or you just grease it when you assemble it and we don't worry too much about the rest. Taper roller bearing, as the picture shows, carries forces both in a compressive axial and in a radial direction. So the force has two components. So if one ball fails, it will typically have a chain effect on the other ones next to it. So if one ball fails, typically what happens is the one element might fail, and then it might make a matching mark in the ring there. So that matching mark will then, as the next ball goes over it, it will make a mark on that ball. And then that ball now also has a mark which will make little mark patterns all around the bearing. And then quite quickly, if one ball fails, the whole bearing will fail because it just will generate roughness on the surface. And these metals are super hard. I actually was very clever once and tried to remove one of these ones from a shaft, but they get press fit on there with like an interference fit. So you have to really whack it to get it off, and I hit it with a hammer and a chip of that shot out and shot into my arm, and it was embedded in there for a couple of months before one day I decided to, okay, today it's coming out. So I started digging, and after some excavation it was removed. These bearings are made of steel, so that's why we do hatch them like steel. Bearing seizure usually means that it stops turning. So technically it could be a bearing seizure because after a while it is going to stop turning. The balls could fail due to age, which would be a fatigue thing, meaning a piece of metal on the surface of the ball actually cracks off. Or it could be due to an impact loading, like you drove the car over a sidewalk at 50 kilos an hour and you just had a force way bigger than what the bearing was designed for. Yes, I'm very glad it wasn't the eye. That I left for the angle grinder. Yes, excavation. Okay, so now you have a good idea of these bearings. So let's quickly have a look at an application of these bearings. I've explained the forces already on my paper, so I don't need to go through this again. Let's quickly have a look at this assembly drawing problem. So this one has a single thrust bearing. I'm just quickly moving all the stuff away on my table. Okay, so at the bottom there, we have a thrust bearing. The thrust bearing has an inside at the bottom of diameter 32, outside size is 60, inside at the top is 30. So it's slightly bigger at the bottom than what it is at the top. To the right of that we have a washer, but this is not a standard washer because it's got a little step in it. Bottom of that washer is 66, top is 78. To the right of that we've got a castle nut. This castle nut size isn't given, but I'm going to assume it based on a logical placement in the drawing somewhere else. You will remember that the size of the head of a bolt or nut is usually 1.5 times, or more or less 1.5 times the thread. So if that's a 46, that must be more or less a 30. Which, if we look at this component, it's got threading with a hole drill to it. Threading with a hole drill through tells me castle nut and split pin, M30. Now something interesting to note, that picture over there, that is my projection symbol. Sorry, I just wanted to check something. Projection symbol says what we see from the left we drew on the right. First angle. So this is first angle projection, meaning this is a bottom view of that component. Okay, so it's circular at the bottom, it's got a diameter of 60, groove in between them of 24. Then this last component, like the body component, has a cone on the inside, small side is 32, angle 70. There we also have a angle of 70, but this time the gap is 30. All right. Yes, in MGC, we're always going to make drawings in third angle. Okay, so basically this shaft comes in here from the bottom, goes through that gap towards the top, goes through this thrust bearing, 32 at the bottom, 30 at the top, matches nicely with that 30, goes through the washer, castle nut and split pin at the top. Now an important thing to note is the, what did I want to say? Oh yes, that cone over there matches nicely with that cone, but we have to think now, if we insert this cone all the way up to the point where it touches that cone, where the two cones meet each other, then the friction will stop the shaft from being able to rotate. Then it would kind of miss the whole point why we have a thrust bearing at the top to allow it to rotate. So I'm going to give a small gap between that line and that line. Yes, everything in this example is in first angle. Where's a 20 diameter hole? Let's see. I don't see a 20 diameter hole. There's a 30. There actually is a needle thrust bearing which has cylinders instead of balls. So the needle thrust bearing does have little cylinders instead of balls. But I'm not going to try and confuse guys with that. Oh, there we go. That diameter 20. That's just a hole that goes through. So this thing is used to attach something to, so that that something can be rotated easily by means of the bearing. So that would just be a functional dimension which we're going to use later on. Okay, so I'm just going to make one view in this assembly exercise because the exercise is more about the assembly procedure than what it is about getting the answer, according to whatever question. So in assembly drawing, I would always recommend that you start with the inside component first and then work your way outwards from there. Okay, there we have the shaft. Now, remember I said this cone of the shaft, I will have to leave a small gap between that cone there. If they are against each other, then it will defeat the whole purpose of this assembly. Okay. There we have a little bit of a pocket, diameter 60, for my thrust bearing to go into. The bottom of the thrust bearing is 32, the top is 30. The thrust bearing is in place. Okay, well in this case I know because I know what the drawing must look like, but when doing any assembly drawing I always recommend doing planning. Okay. That pocket is 60 millimeters in diameter, same as the bearing outside. The little pocket is 4 millimeters deep. We're not specifically given the bottom size, the top one is 6. So it means the bearing is not the same depth as the pocket, it's slightly taller. Slightly taller over there. Then that total height from there to there is 20 plus 4, so that's 24. The bearing has a thickness of 21. That washer with the 66 part has a thickness of 4, so 21 and 4 is 25. Okay, that means the washer, if I put the washer in place, will be slightly wider than the bearing, and then it will go up. 4 millimeters. Then it becomes wider again up to 78. Something like that. So in this case, no taper bearing or the thrust bearing will both do the same job. Yes, your explanation is pretty good. So no, there won't really be a tapered ball bearing. You do get an angular contact ball bearing, which does something similar to what you are referring to. A washer is normally a standard component, but that's normally if it is just a flat washer. This one is not a flat washer. Okay, so if we check that diameter is 60, then it goes up to 68. This is 66, so it will be 1 millimeter wider each side. And remember now that 4 and that 21 add up to 25. Those two add up to 24, meaning the little ledge of the washer will overhang over there by 1 millimeter. Then the top diameter is 80. This washer is 78, so that's 1 millimeter again. Now I'm just quickly going to add my castle nut. something like that. Okay, so the washer has a 1 millimeter gap and then a thickness of 6. That is 15, so it's 8 millimeter gap between the top of the washer and the top of that base component. And then we can just quickly copy the rest of the profile. And to show some more information, I'm just using a little broken out section to show the groove that goes through on this axle or shaft component. Okay, so in the question, the split pin was not given, but it is a standard component, and many times standard components are not given in the question because they are standard. Yes, as the next student has pointed out. Okay, good. So this is basically just the assembly of these components. I didn't hatch the balls because they are solid, so there's no point in cutting them open to show that there's nothing on the inside. We know there's nothing on the inside. Okay, if you have any more questions or any questions, you're welcome to ask. Okay, so the castle nut means that your shaft can now have a ledge on it. So you can assemble it and have a ledge, and then you keep the ledge in place with the split pin. So the castle nut rotates with the shaft so that as you spin the shaft, you don't undo the nut at the top. And then the bearing is what is used to reduce the friction when turning. So the castle nut and split pin are there to prevent relative rotation between a nut and a shaft, which is in this case what we want. But we do want relative rotation between the shaft and the body.